Hello, student. Welcome to this chapter of alpha decay. And in this session, we'll see what is this Geiger-Nuttall law. Geiger and Nuttall in 1911 discovered an empirical relation. sorry. Uh, Discovered an empirical relation between the ranges of the alpha particles and the disintegration constants of the naturally alpha active substances emitting them. This is known as Geiger-Nuttall law, which can be expressed as log lambda is equal to A plus B log R, where this lambda is called as the disintegration constant. uh, that means how many number of particles are emitted by a radioactive substance per unit time is called as the disintegration constant, and these A and B are the constants, and R is the range of the alpha particle. In the last session we have discussed what is this range of the alpha particle. So range is the distance traveled by the alpha particle either in a solid or in a gaseous medium before it loses its all energy. So according to this law, the alpha particles emitted by substances having larger disintegration constants are the shorter half-lives, because lambda is equal to this lambda disintegration constant and the half-life t half, they are reciprocal to each other. So that is why according to this law, the alpha particles emitted by substances having larger disintegration constants or shorter half lives have longer ranges and vice versa. This is very clearly seen in this equation 1. So this is the range of the alpha particle, and as these two are constants, this disintegration constant lambda is directly proportional to the range of the alpha particles. So this is referred as the Geiger-Nuttall law. So from equation 1 shows that if you are plotting a graph of log lambda versus log r, it's a straight line with the slope b. So this is a graph, and for a different radioactive series, different straight lines are obtained, which are parallel to one another, so that the slope b is the same for all of them, as shown in the diagram below. So this is the diagram, or it is the plot. It is the graph plotted log lambda versus log r. Here we have obtained the three straight lines, because this Geiger-Nuttall law, which is given by log lambda is equal to A plus B log R. So that is having a standard equation for, that is having the form of the standard equation for a straight line y is equal to mx plus c. We have studied in mathematics, where m is the slope of the straight line and c is the y-intercept. So in the same way, this equation is there. This is log lambda is equal to a plus b log r. So that is why we have obtained the straight lines here. And these three straight lines are for the different series of the radioactive compounds. The first line is called as the actinium series. That means, for example, this actinium compounds gives this straight line, and this is the thorium series straight line. For example, THC dash, it is THC dash, that is the thorium and the isotope of carbon. When they are combined together, they become the sources of alpha, and similar. So for such compounds, we have got this relation, this straight line, and this is another straight line for the radium containing compounds. So, and all these straight lines are parallel to each other, indicating that their slope is parallel, is equal. They are of equal slopes. So equation 1, from equation using equation 1, it is possible to determine the disintegration constant and hence the half-life of a radioactive substance if the range of the alpha particles emitted by it is known accurately. So this is the use of equation 1 or the Geiger-Nuttall law. That means if we know the range of the alpha particles, we can calculate the disintegration constant lambda and the half-life of that particular radioactive element. Next, so while studying the range of the alpha particle, we know that R is proportional to E raised to 3 by 2. Range. Range of the alpha particle is proportional to energy E raised to 3 by 2. And by taking log on this equation, we will get log R is equal to 3 by 2 log E, and so then equation 1 can be written as that means in equation 1 this log R is there, that can be replaced with this log E. So equation 1 becomes log lambda is equal to C plus D log E. So obviously this D is equal to 3 by 2 because of this, and C is another constant. So this is the another form of the Geiger-Nuttall law in terms of energy. Next, we will see what are the characteristics of alpha ray spectra. It is known that the alpha particles emitted by a radioactive substance are usually monoenergetic. That means they will be having the same energy. This shows that they are emitted from one definite energy state of the parent nucleus to a definite energy state of the product, as the energy is a single energy. But what happens in the case of some nuclei, means radioactive nuclei, more than one group of alpha particles, each of a definite energy, are found to be emitted by the same radioactive substance. This can happen due to the transitions from the different discrete states or excited or ground states of the parent nucleus to the different discrete states of the product nucleus. Such transitions are grouped into uh, two, two classes. Class 1, in the class 1, we are dividing this class as a long range alpha particle. So in this case, the transitions takes place from the different excited states of the parent nucleus X, which has mass number A, to the ground state of the product nucleus Y. It is Y is called as the product nucleus, which is having mass number A minus 4, as shown in the figure, thus in this figure. So the energies the energies The energies of these particles, that is E alpha dash, E alpha double dash, are obviously greater than the energy E alpha of the main group of alpha particles produced by the transition from the ground state of the parent nucleus to the ground state of the product nucleus. So you can see here, these are the different discrete energy states of the or energy levels of the parent nucleus, and this is the ground state of the product nuclei. So many transitions are taking from these discrete states to the ground state of the product nucleus. So for example, this transition is there, this particular transition. So this particular transition is taking from the highest excited state of the parent nucleus to the ground state of the product nucleus. So the energy gap or the energy difference is high, and obviously the energy of this or particles, alpha particles emitted because of these transitions will be more. Next transition is from the first excited state of the parent nucleus X to the ground state of the product nucleus Y. So the energy difference between the first excited state of the parent nuclei and the ground state of the product nuclei is less as compared to the first transition. So the energy of the alpha particle which are emitted in these transitions are E alpha dash. So obviously this energy is less than this energy. Next, look at the third transition which is taking place from this ground state. This is the ground state of the parent nucleus. So from the ground state of the parent nucleus, there is a transition to the ground state of the product nucleus. So the energy difference between this state and this state is less as compared to these. So obviously the energy of these alpha particles will be less as compared to these two. So in this way, uh, the different alpha particles with different energy are emitted because of the various this kind of transitions. Suppose if in this process, if the parent nucleus is taking some transitions between its own states, then there will be emission of the gamma particles or gamma rays. For example, here the parent nuclei is taking a transition from its own highest energy state to the first highest energy state, then this gamma particle will be released. And here from higher energy state to highest energy state to it's a ground state, uh, and the transition is there. So here gamma particles of highest energy will be reached, and this is again another such a transition from first excited state of the parent nucleus to the ground state of the parent nucleus. So here also gamma rays are produced. So in general, the gamma rays are produced if the parent nucleus is taking the transitions from taking the transitions within its own energy states in this way. And if the transitions are between the parent nucleus, uh, if the transitions are from different states of the parent nucleus to the ground state of the daughter nucleus or the product nucleus, then alpha particles of different energy will be released. But it is found that these alpha particles which are emitted due to the transition from ground state of the parent nucleus to the ground state of the product nucleus are called as the mainstream alpha particles or main group alpha particles, because these alpha particles are highest in number, or we can say that this is the most probable transition between these two states. And these two alpha particles, even though that kind of transitions are possible, but the probability of these transitions is very very less as compared to this transition. So that is why the alpha particles, which are having higher energy than the mainstream alpha particle, will be generally less in number. So, and these are called the long range alpha particles. That means in this figure, E alpha double dash, E alpha dash, comma E alpha double dash 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 dash, they are called as the long range alpha particles. Their transitions are small compared to uh, their transitions are, sorry, their transitions are small compared to the intensity of their intensities are small compared to the intensity of the main group. They are observed in the alpha disintegration of the isotopes of uh, radium clubbed with C dash, means the isotope of carbon, and thorium carbon compound. And this kind of compounds, there is a emission of the alpha particles, or alpha disintegration will be there. So this is about long range alpha particles. Next, we will see what are the short range alpha particles. So in some cases, alpha emission takes place from the ground state of the parent nucleus Xa to the different states of the product nucleus Ya minus 4, as shown in the figure. So we can see here, this is the ground state of this parent nucleus, and these are the different energy states of the product nucleus. So the transitions are from ground state of the parent nucleus to the different energy states of the product nucleus. If the product nucleus is formed in an excited state, in such a transition, it subsequently emits gamma rays to make a transition to its ground state. So here, as I explained in earlier case, suppose if the this product nucleus is in a different excited state, then it will take a downward transition to its ground state by emitting the gamma rays or gamma particles. So different gamma particles of different energy are emitted when this daughter nucleus or the product nucleus take the transitions from different excited states to the ground state. So the probabilities of the emission of the different alpha ray groups are making the fine structure of the alpha particles. So together, that means including the long range alpha particles and the short range alpha particles, when you are clubbing all these, you will get a variety of alpha particles which are having a different energy. So that means it forms the fine structure of the alpha ray spectra. So this is about the Geiger-Nuttall law and the spectra of the alpha particles. Thank you.